in the last video, we were thinking about this sort of pogo stick example, and we were interested in modeling the phase of motion during which time the pogo stick is in contact with the ground. We decided that our system boundary included the person and the stick, and we chose to model the system as simply a point mass attached to the ground via this funny spring. We identified a set of interactions that were important, the sort of spring force that the ground exerts back on the person and stick combination, and the gravitational force that acts at the center of mass. And then finally, we identified what coordinate system we wanted to use to describe it. So we're interested in both what the angle of the pogo stick is relative to the ground, and also in how long the pogo stick is, and potentially also in what the length of the person's arm is, that is how far they push themselves away from or pull themselves toward the stick. So we've identified coordinates, and we've identified parameters. Okay. Now at this point, we need to get a little bit more explicit about the mathematics. So one of the first things to do from a mathematical perspective is to go from having defined that coordinate system and define the free body diagram to figure out what the mathematical models are for the forces. So let's try to write what those forces are. Well, pretty clearly the gravitational force is an easy one to write, right? It's minus mg j hat. Okay, so it's down. The spring force is also not terribly hard to write if we choose to use a polar coordinate system. So the spring force here, it would be a spring constant times the length of the spring, the difference between the spring's rest length and the actual length of the spring, and it would be oriented in, I'll say, the d hat direction, where d hat indicates the direction along the actual spring. So notice that d hat is along the spring. Theta hat would be a unit vector that's perpendicular to the spring. And if I think about this expression, let's check if the signs are right. When the length of the spring is greater than the rest length of the spring, this term is negative. That means the force is down, which actually says that, which is a case of the pogo stick actually being pulled into the ground, which would be true if the pogo stick were actually pinned. The more interesting case is actually the case where d is less than d naught. When d is less than d naught, this ends up being positive, and the person gets pushed away from the ground. So we actually might say that the force of the spring is k times d naught minus d in the d hat direction, if and only if d is less than d naught, and it's 0 otherwise. And in fact, this will be the condition for transition to flight. Right? So basically, you're only in contact with the ground when the pogo stick is actually shorter than its rest length. Okay, so now we've got mathematical models for both the gravitational force and for the spring force. I will put a little warning here, which is that j hat is not perpendicular to d hat. Right? We need to be very careful about unit vectors here. We're actually mixing, we're sort of doing a semi-natural coordinate system where we're mixing j hat and d hat, and that's going to be something we're going to have to think about more carefully in a little while. All right, so now we've figured out how we're going to write the forces. We now need to think about how do we actually go from that mathematical model for the forces to asking the question, what are the differential equations? So we'll start with the sort of generic version of this. So time rate of change of the momentum of the system is equal to the sum of the forces, right? That is the generic equation of motion for particle motion. It'll apply for pretty much any situation that you're interested in. All right, but now let's think about this left-hand side a little bit. This left-hand side is a little bit more interesting. The right-hand side initially is not so interesting, so maybe we'll start with that. Actually, let's start with the less interesting part and write out the right-hand side. So the right-hand side, we have a gravitational force, minus mg j hat, and we have a spring force, so plus k times d naught minus d in the d hat direction. Okay, so that's gravity, and that's the spring force. On the left-hand side, on the other hand, we need to take a derivative of the momentum, which requires that we actually think about how do we express the momentum for this coordinate system. Well, the momentum for this coordinate system is the mass times the velocity of the object, which really requires we come back here to our definition of the coordinate system and think about how do we think about the velocity of the object? Well, the vector of interest is the location of the center of mass, right? So I'm going to call that vector x vector, right? And x vector in this case, right? So I'll draw this again just so we can have something to work with. This is D, this is L, and x vector I could write out as d times d hat plus L times theta hat. Right? So I'm using the sort of idea of polar coordinates here. I'm walking out d in the d hat, or what I could also call the r hat direction, and then walking L in the theta hat direction in order to get to the location of the center of mass. Okay? What does that mean my velocity is? Well, my velocity is the time rate of change of my position vector, right? And let's think about what things are changing in time here. Well, d is changing in time. D hat is changing in time. L, let's assume the person is not changing the length of their arm. So L is not changing in time. Theta hat is changing in time, right? Because presumably the angle of the stick with regard to the ground could be changing in time as well. So that means we're going to get here we'll have to apply a product rule. So I'll get d dot times d hat plus d times theta dot times theta hat. Note that d hat is basically the same thing that we've called r hat previously, so the derivative of that is theta dot theta hat. And then we also are going to get a minus L times theta dot times d hat, because the derivative of theta hat is minus theta dot r hat, or minus theta dot d hat in this particular case. Okay, so that means my momentum is m times d dot d hat plus d theta dot theta hat minus L theta dot d hat. And finally, if I take the derivative of that, my acceleration times my mass, or my derivative of momentum, is mass times, and then we get a lot of terms. And a lot of these terms should look very familiar, right? For example, we get a d double dot times d hat term. We get a plus 2 times d dot times theta dot times theta hat term. We get a minus d times theta dot squared times d hat term, right? And we get a plus d times theta double dot times theta hat term. And then finally, from this second term, the L term, notice we're going to get a minus L times theta double dot times d hat and a minus L times theta dot squared times theta hat. Okay. And let me check if I kind of got that right. It's always good to check your math. This is negative. Theta dot gives me theta double dot. D hat derivative gives me theta dot times theta hat. So that should be a negative, that should be a negative, and the only negative term that I should pick up from the first is the centripetal term that's in the minus d hat direction and goes as d times theta dot squared. So, okay, that looks sort of believable. All right, that is my left-hand side of my equation of motion. Right? That has to be equal to the right-hand side of my equation of motion, which is minus mg times j hat plus k times d naught minus d times d hat. Okay? And now I get to the point where I need to make all of my vector choices consistent. On the left-hand side, I've got d hats and theta hats running around. Those two vectors are orthogonal, and so I can collect all the d hat terms and say the only way that this can be true is if all the d hat stuff on the left equals all the d hat stuff on the right, and all the theta hat stuff on the left is equal to all the theta hat stuff on the right. On the other hand, on the right-hand side, I have two non-orthogonal vectors. I need to either choose to work in I hat and j hat on both the left and the right-hand side, or in d hat and theta hat on both the left-hand side and the right. And I'm going to choose to work in d hat and theta hat because I've got so darn many d hats and theta hats, and I just have this one annoying j hat running around. So let's convert that. So I'm going to convert the right-hand side to be minus mg, and j hat, if I think about it, is going to be a cosine of theta times theta hat, right? When theta is 0, j hat is in the plus theta hat direction. And similarly, when theta is pi over 2, it's in the plus d hat direction. So j hat is cos theta theta hat plus sine theta d hat. And then my other term, of course, is still k times d naught minus d times d hat. Okay? And this is my right-hand side. And at this point, you can see now I've actually got a left-hand side that has theta hats and d hats, a right-hand side that has theta hats and d hats, and the only way that I can actually satisfy this vector differential equation is so all the theta hat stuff on the left equals the theta hat stuff on the right, and all the d hat stuff on the left equals the d hat stuff on the right. I will spare you the algebra and simply pause this video here, and then I'll make one more video that actually walks through what the solution, what the sort of algebraic manipulation of this yields. But this is sort of the key idea, is this idea that you have to figure out how to write all your accelerations in the same coordinate system as you write your forces in, and then make appropriate equivalencies along each of the unit vector directions.